right, everybody. Hope you guys are having a good Wednesday morning. Today we are going to review a paper called Beyond Surface Statistics, Scene Representation in a Latent Diffusion Model. Now we are awake. Here it is 3 p.m. Here it is 8 a.m. All right. So this paper is actually not even a published paper. It's what's called a preprint. So a preprint is basically you post the paper directly on arXiv, or maybe you just release it on some other social media website, and you haven't gotten it formally through the review process and then been published in a journal. So normally that should set off alarms because it means that it hasn't gone through this review process, which means that the academic peer review system hasn't necessarily vetted that what they're saying is correct, but in machine learning is not very unusual to do that. It moves so quickly that preprints are generally fine, and especially preprints from an institution like Harvard. These people probably aren't lying. This is probably totally fine. And it was at the top of one of the machine learning subreddits. I think it was the Stable Diffusion subreddit. But it seemed pretty cool, and more than that, it's kind of like a investigation paper. So what do I mean by that? There are some papers that they basically try to introduce some kind of new algorithmic thing, and then there's other papers, and here our work fits into a long line of interpretability research. There's other papers where they basically just kind of dissect something, and they take it all apart, and they kind of look at what all the different pieces are doing. And I think this is one of those papers. And in this paper, they're basically going to dissect a latent diffusion model and kind of probe at it and see what's going on inside this latent diffusion model. So I generally love these kind of papers because these are the ones where you kind of learn the most and get the best intuition. You know, you get a lot more intuition from these dissection papers than you do from the papers that propose something new and then just say, hey, it seems to magically work and here's the benchmark and why it's better. So that's kind of why I picked this paper. So 9 June 2023, so maybe a little bit older at this point, but this is also the preprint, so we'll see that. Let's get right into it. Abstract. Latent diffusion models exhibit an impressive ability to produce realistic images, yet the inner workings of these models remain mysterious. Right? Latent diffusion models are diffusion models that operate in the latent space, so they don't diffuse in the actual image space, they diffuse in a latent space which is created by a VAE, which is based on a reconstruction loss. Even when trained purely on images without explicit depth information, so here they're saying that your average latent diffusion model, neither the diffusion model nor the latent model has ever seen a depth image, right? Depth image, if you're watching this channel, you definitely know what a depth image is, but just in case some of you are new, this is what a depth image is, right? A depth image is a one-channel image, so it's not RGB, it doesn't have red, green, and blue values. It basically is just a single value for each pixel, and that value represents how far away something is from the camera. This looks like an RGB image, but this is just a recoloring of depth information just so it's easier to read. But normally a depth image is a single channel, right? And they're saying they typically output coherent pictures of 3D scenes. In this work, we investigate a basic interpretability question. Does an LDM create and use an internal representation of a simple scene geometry? Or another way of thinking about that is, can we understand the internal representations of a latent diffusion model, right? Because it used to be the case that the way that people did machine learning and computer vision was they would do feature engineering. So people would design these manual features, such as I like to bring the example of SIFT. Maybe not. Let me try orb. Orb and SIFT. Yeah, so these are manually designed features based on basically these vectors, scale invariant feature transform, and then oriented something something. But these are manually designed features that you can explain 100% and understand 100%, and those are useful for downstream tasks such as classification or detection or tracking or anything like that, or correspondence. But as soon as we went into this deep learning paradigm where we started using neural nets for everything, we kind of lost that interpretability, that kind of ability to know exactly what these features mean. And if you cut a neural net in half and just look at the representation internally, a lot of times it's very difficult to interpret. So in this paper, it's not that there isn't some kind of internal representation within this diffusion model or the VAE that creates that latent. It's just that it's very difficult to interpret, and that's what they're going to try to do in this paper. Let's see, you guys got some questions already. There is no transformer in a unit. Yes, the VAE is generally... actually, I don't know what these VAEs are at this point. I assume there's many different types of VAEs that they use. They'll probably tell us which one they're investigating here. Well, if it's conditioned, transform with a unit. Yeah, and this is not necessarily the first time people have done this. There was a very... I'm never going to find it. During the early days of deep learning, people did this with convnets, and they looked at the internal activations of a convnet, and you got all kinds of interesting things. Let me see if I can type inside a convnet. No, I'm never going to find this. I forget the exact keyword. I want to say deep dream or something like this. No. Maybe one of you guys know that. Okay, but anyways, back to the abstract. Using linear probes, we find evidence that internal activations of the LDM, so a linear probe, they're just talking about a linear projection of some of the internal representations of the LDM, but you can think of this as they're basically dissecting this frog brain, and then they're taking a little probe, and they're just putting it halfway through the frog brain and seeing what they find. We find evidence that the internal activations of the LDM encode linear representations of both 3D depth data and salient object and background distinction. Okay, so they're able to look at these representations and see something that looks like depth and something that looks like foreground-background classification. These representations appear surprisingly early in the denoising process, well before a human can easily make sense of the noisy images. Intervention experiments further indicate that these representations play a causal role in image synthesis. So these representations are not just there, but also ultimately leading to the ability of these diffusion models to generate images from text conditioning, and may be used for simple high-level editing of an LDM's output. And this is kind of the application. Well, okay, if you can understand these intermediate representations, then maybe you can manipulate these intermediate representations, edit them in some way. And let's get to it. Latent diffusion models, or LDM, are capable of synthesizing high-quality images given just a snippet of descriptive text. They're conditioned on text is normally how that's called. It remains a mystery how these networks transform, say, the phrase car in the street into a picture of an automobile on the road. I don't know if mystery is the right word. I think we understand all the different parts. We maybe don't understand what every single neuron is doing, but we have a general idea of all the different pieces in that system. Do they simply memorize superficial correlations between pixel values and words, or are they learning something deeper, such as an underlying model of objects? We investigate whether specific LDM goes beyond surface statistics. Okay, so that's where the name of the paper comes from, right? Is it surface statistics, aka correlations between pixel values, or is there something deeper that it's finding there where the representation that it builds is actually analogous to our own semantic hierarchical breakdowns of our reality? we asked whether LDMs create internal 3D representations it portrays in 2 dimensions. To answer this question, we apply the methodology of linear probing. Okay, to a pre-trained LDM. Our probes find linear representations of both continuous depth map and a salient object background distinction. Continuous depth map. Continuous there means that the values are continuous, right? This is a continuous depth map. You see how you have everything from this white color all the way to this black color. You kind of have this continuous. This is especially noticeable here on the floor, right? Because you go through the whole spectrum of depth there. Sometimes they're not continuous, right? Foreground, background, you could almost think of it as a discontinuous depth map. Intervention experiments further revealed the causal roles of these 2 representations in the model output. Our work fits into a long line of interpretability research. The general question of whether generative neural networks can be characterized as merely aggregating surface statistics, with some evidence suggested they do build world models. So interpretability research is also a big thing, I guess, in language models. NLP, as it's called in its historical name. Investigations of image synthesis systems are less numerous, but suggest internal representations of scene geometry may play a role. Recent works leverage pre-trained diffusion models as priors when optimizing a neural radiance field for 3D generations. So we've seen this a million times, but you take the representations trained for something else, such as a VAE, you're learning a representation that's useful for reconstruction, and then that representation turns out to be useful for a diffusion process, right? We've seen how clip, which is a contrastive loss, right? You're using a contrastive loss to train this kind of joint embedding of language and images, and then that joint embedding ends up being extremely useful for a bunch of downstream things. Independent as a part of effort to steer denoising diffusion probabilistic models. Kim et al. Found evidence of a complex nonlinear representation of depth. Section 6 discusses this. Our findings is that a simple linear representation of 3D geometry plays a causal role in LDM image synthesis, providing additional evidence that neural networks learn to create world models in context of image synthesis and offer a basis for further study of the issue. So I think the key word here is causal, right? Is that they're not just going to go in and say, okay, we see something that kind of looks like depth, but then they're probably going to start messing with it and showing that by messing with this notion of a semantic depth that's buried inside this LDM, they're going to be able to change the image generation in a way that makes it seem like there is kind of a causal relationship there between the internal representation of depth and the actual final image that is created. Okay, we have a nice little pretty picture here. We have a bunch of steps. So obviously these diffusion models, they don't remove the noise all at once, right? They remove the noise over a series of subsequent steps. I love to bring up this image. Diffusion model. Where is it? Yeah, this picture. I feel like this picture kind of explains diffusion models super clearly. But let me open image in new tab. But right, you start from here. You start from pure noise, and then over a series of time steps, you eventually get to this picture of the dog, and you can see how kind of this dog emerges from the noise. So there's a similar thing kind of happening here, where, let me close this, where this image of this automobile is emerging. Okay. LDM has an internal representation of depth and saliency that develops in the early denoising steps. Okay, so saliency, have you ever seen a saliency map? This is when you do this same kind of idea of like going backwards through each of the representations inside a, for example, in a ConvNet. Here's a good example. Open image in new tab. Maybe this is the pictures I was trying to find, but this is what the representations inside a ConvNet look at the lower layers, so the early layers, and you can see how they're kind of just simple things like oriented edges. Like here you have what look like oriented edges, circles, and these features are going to trigger on specific things in the image, right? And as you go higher and higher up into the ConvNet, they become more and more semantically understandable. You know, these are kind of maybe a little weird, but eventually you get to the top and they start looking like things that you would recognize. But you can then take these ConvNets and then say, okay, well, let's go backwards from this brushing teeth, which might be the final actual output. Maybe this is classifying activity, right? So you have some activity classification convnet that tells you in this picture what is happening. Is someone cutting a tree? Is someone brushing their teeth? Is someone painting a house? And then you go backwards from there and you say which parts of the image had the highest activation that ultimately contributed to me classifying this as brushing teeth. And if you go all the way back, you can get these saliency maps, which are overlaid here on top of the real images, and you can see how what's leading to the ultimate decision of this being classified as brushing teeth versus cutting trees is this person holding the toothbrush. So it's like the features related to the mouth and the toothbrush and holding the toothbrush, those are what are causing this to be classified as brushing teeth. Same thing for the cutting trees. It's obviously, you see how it's focusing on the hat, right? So it's kind of determined that anytime anybody's cutting a tree, they're almost always wearing a hat or some kind of construction helmet, and therefore if I can see a construction helmet and I can see a chainsaw, it's someone cutting a tree. So that's where saliency comes from, that develop in the early denoising steps. Early denoising steps, right? And I think the early there is key, where they're not saying that, hey, you can look at this picture here and there's some notion of depth here, but they're saying actually here, when it looks like noise to us, there's already an internal representation which has an idea of like what is going to be the foreground, what is going to be the background, where are the edges, and so on. Row 1 is the decoded image. So decoded here refers to the fact that the denoising is happening on the actual latent representation. So if they were just to show us the latents here, it wouldn't look like anything. It would be very difficult for us to interpret. So they've fed each of the intermediate latents into the decoder of this VAE in order to give us an image that we can see. Row 2 and 4 are predictions of probing classifiers. So a classifier trained on a specific layer, right? So they cut this neural net in the middle and then they just train a classifier just on that middle. Let's get a little neural net out here. So a probing classifier would be basically you have your little neural net, you cut it right here, and then you train a classifier on this. What do you get? And then you can train a classifier on that, and then you can look at the saliency map for that. And that's kind of what they're doing here. Row 3 and 5 are baseline predictions from off-the-shelf models that take decoded RGB images decoded at each step as input. Okay. Rows 3 and 5. So, salient object from image. I guess what they're showing you here is that there's nothing in these initial steps, and then it kind of appears at the end. Salient object from internal representation, there is something there, right? So they're saying if you just took this image here, this image that looks a little bit like noise to us, and then fed it through something that detected the object in it, it wouldn't find anything, right? So object detectors are unable to find the car in this. Depth models are unable to predict the depth from here. But if you train a linear probe from these images, from these early images, you do have the representation which shows up. And kind of what they're trying to show you here is that this internal depth representation and that this internal objectness or foreground background representation here with this mask, they are appearing very early on in the diffusion process, right? So even though it looks like nothing's happened here and it's all noise and the car doesn't start appearing here, the diffusion model already has an idea of like, here's kind of where the wheel is going to be, and there's going to be an object and it's going to kind of be facing this way, and here's kind of vaguely where the object is going to be. What's the difference between DDIM and DDPM? DDIM is discrete. I'm not actually sure about that. DDIM versus DDPM diffusion. You know what? DDIM, denoising diffusion implicit models versus denoising diffusion probabilistic models. DDIM are more efficient and iterative. DDPMs are, I guess, slower, take more samples. also have a consistency property. This means that if you start with the same initial latent variable and generate several samples, the samples will have similar high-level features. DDIMs perform better than DDPMs when the number of steps taken is less than the original T steps. Okay, so basically DDPMs are better, but they require more time steps. DDPMs are refined as the reverse of a particular Markovian diffusion process. Markovian is just the Markov decision process. It's basically like this formal sense of you have states, you have actions which move you between those states. Taking the same action, you end up at the same state. And this is the core underpinning behind a lot of reinforcement learning. But MDP is basically this graph here, right? You have states, actions, and so on. But maybe going back to your question here. Here's a little understanding DDPMs. Oh no, we have to pay. Fuck that. Changeable, maybe Yujun has the answer for us here. Changeable sample schedule, and a formula concludes lambda parameter, which can be shifted to DDIM sometimes. It seems like all we're getting here is like difference between DDPMs and DDIMs, but in order to answer your question better, we would have to like look at the exact equation here. Okay, so this seems fine. DDPM, that seems like pretty generic. What about DDIM? Improving DDPMs, optimizing the variance, DDIMs. Speed of generating. We may be able to produce, but takes 1,000 model passes. Passing an image through a model 1,000 times, blah, blah, blah. DDIM introduces a way with little image quality. It does so by redefining the diffusion process as a non-Markovian process. DDPMs are Markov chains, okay. Meaning that an image at time t cannot be generated until the entire chain before t has been generating. Okay. So in order to get to the next state, you have to basically get to the previous state, which is probably why the DDPMs take so much longer. Makes the process non-Markovian, allowing you to skip steps in the denoising process, not requiring all past states to be visited before the current state. Okay, so basically they do some little math trick to reinterpret it as not a Markovian process, which means that they can do it in less steps, but it seems like the quality is lower. So since there is no noise, the process is deterministic, and we no longer have a Markov chain, since Markov chains are used as a probabilistic process. So here's the DDIM denoising, and there's no added noise. So there's no noise term here, versus in a DDPM, you do have the noise. Here's your Gaussian. Okay, so DDPM is Markovian, has noise, therefore you need to evaluate every single step, because to get to one step you need the previous step. DDIM, there is no noise, it's not Markovian, therefore you can skip steps, but it doesn't quite work as well as DDPM. Is that a good enough summary? Maybe? Maybe a good summary, maybe not a good summary. Okay, hopefully that is good enough. DDIMs use no random noise. Yeah, that's what they said here. Okay. Thank you. I appreciate it. I'm glad you liked my response. Background, stable diffusion. We chose stable diffusion because it's an open source text image diffusion model. Okay, all of our experiments were conducted on stable diffusion v1. It's a little old, but it checks out. I think it's still largely the same. Trained without explicit depth information. Note that we did not use the subsequent version, which incorporated depth as a prior. Stable diffusion is a two-stage image generative framework that consists of the LDM, the latent diffusion model that actually predicts the noise and then allows you to remove that noise. Let me actually use 4 for that. That's the it's a mathematical definition there. And then the variational autoencoder, the VAE, which goes from image space into this latent space and back and forth, right? You have the two pieces of that. You have the decoder and you have the encoder. The encoder takes you from image space to latent space, and the decoder takes you from latent space to image space. VAE. Here we go. You got your encoder, you got your decoder. This one's actually a little bit more annoying. I think this is better. Actually, this is even better. Encoder, decoder, input, output, latent space. It learned to generate images from noisy observations by reversing a forward diffusion process. The forward process, the encoder of the VAE, compresses an RGB image X, a 3-channel image with some height and width, right, into some latent variable Z, which is smaller, right? The whole point of these latent variables is that they're smaller, which means that diffusing takes less compute and memory, right? So all of this is just about saving compute and memory, is why we use a latent diffusion model rather than just a diffusion model in image space. So you can see how rather than h by w by 3, it's now h over m, where m is going to basically make that h and w smaller. That resides in a low-dimensional space. The forward diffusion transforms z into a normally distributed variable via Gaussian transition. Okay. The LDM E of theta epsilon theta is trained to predict the noise added during the forward diffusion. In the generative process, epsilon theta synthesizes a latent by progressively denoising a sampled noisy observation. So your z at time step t, which is at the very end, right, at the very end of your diffusion here, it should be pure noise, and that's what they're saying here, right? It should be normally distributed with a mean of 0. The decoder of the VAE converts the denoise latent back to the image space. To allow conditional sampling, which is, okay, maybe I want to generate the Z, but I want to condition that on something, this Y. So you could condition it on text, you could condition it on a specific class, you could condition it on anything you want. The LDM fuses contextual embeddings, TY, so whatever it is you want to condition your diffusion model on, you also encode that, right? So tau here is the encoder for whatever this Y is. So in our experiments, Y is the actual text, and then tau is the actual encoder for that text. So in this case, the clip text encoder. You guys are still talking about DDIMs and DDPMs. I tried DDIM and DDPM. They're both not work so well compared to stable diffusion. Well, there is noise in DDIM, but only at x0. I can't recognize the denoising image after training. DDPM should be better than LDM, just takes longer to train because there is no latent space with DDPM. Is there? I think the Alright, I'm gonna close my mouth because I might just sound stupid there. Probing classifiers are used to interpret the representation learned by deep neural networks. Borrow this technique to investigate whether an LDM builds a representation of per pixel depth. Right, so they're going to train a classifier to predict the depth at every single pixel. Probing classifiers take the intermediate activation of a neural network, aka just intermediate activation just means the values of this layer here, so they're kind of like surgically cutting it and then using the values of this intermediate representation to infer some properties. We define the intermediate activation as the model's internal representation. A high prediction accuracy indicates a strong correlation between the learned representation and the predicted property. So if you can train a classifier, I'm like all over with these colors, if you can train a classifier on these intermediate representations, and they actually work quite well. So in this case, they're training a classifier for depth, for per pixel depth. Then there's probably something going on in that learned representation that is very, very similar to depth, right? It's in effect that internal representation is depth. Yeah, Chris, I just don't know if, I think you can use both. I think you could use DDPM or DDIM for the latent. Whether or not you're using a latent or the image space, I think is separate from whether it's a DDPM or a DDIM, right? Let's see. Let's ask GPT. Can I use DDPM and DDIM diffusion processes on both latents and image space? Yeah. So the latent part is separate. Whether or not you actually do it in latent space or image space is separate. Let's see what it says on DDIMs though. Okay, it's actually going to go through all 4 of them. Let's give it a second. The probing classifier may find spurious correlations when the model has an enormous feature space. To quantify the strength of the correlation by the classifier P, previous works test P on internal representations of a random untrained model in addition to the trained version. So a model that hasn't received any gradients. So you basically just take the latent diffusion model before it's received any gradients. It's just the initialized weights, whatever they are, and then you train the classifier on that same internal representation at that point in time. And then if it's about the same, then it means that really the classifier is just able to find the signal in the noise, not so much that the learned representation is depth. Let's go back to ChatGPT here. Okay, DDIM improves sampling technique for DDPM. Instead of sampling only at the final time step, DDIM samples from intermediate noisy images. This can result in faster and more diverse sampling. Right, we keep seeing these same things come up again. Faster, non-Markovian, skipping steps, not quite as good. Applying DDIM would follow the same principles. Instead of sampling, you'd sample from intermediate latents. But it's called a latent diffusion model. Yeah, I mean, you're picking, right? There's like 50 different words that you could use to talk about this latent diffusion model. You could call it a VAE diffusion model. You could call it a latent DDPM diffusion model. Like at some point they're just picking the word latent just because, you know, an LDM is just a diffusion model in latent space, and they're deciding that the fact that it does it in latent space is more important than whether or not it uses DDIM or DDPM. Okay. High probing performance does not imply a causal relationship between the representations and the property of its outputs. To uncover a causal link, recent works use the projection learned from P to modify the internal activations and measure the effects on its outputs. Okay. So that's basically what they're going to be doing. They're going to be training a classifier on an intermediate representation of this LDM, seeing if you can get this classifier to predict per pixel depth better than the untrained version of the model. Okay, so probing for discrete and continuous depth, where continuous depth is not continuous because, right, any time you're doing this, this is not infinite precision here, right? This is like probably a uint 8, which has a limited amount of values, right? So in a way it's discrete. It's just that it's discretized into like 256 possible depth values. But you can imagine if you had some float data type with infinite precision, that would be your continuous depth. Stable diffusion often creates scenes that appear to have a consistent 3D depth dimension with regions arranged from closest to farthest relative to a viewpoint. Okay, it's able to create images that appear realistic in their depth. Beside this continuous depth, we also see images with bokeh effects. Bokeh effects are the little triangles you see. Let me see. Yeah, this thing. So you can make them whatever arbitrary shape you are because it's related to the shape of your camera aperture. So that's why you can make bokeh appear triangular or appear circular. Most of them are circular because most camera apertures are circular. They have like a little iris lens. But you can make them triangles. You can make them whatever you want. Here you have a nice little heart bokeh. Where some objects are in clear focus and their background surroundings are blurred, we therefore explored the world representations of depth from two perspectives. A discrete binary depth, aka foreground background, certain attractive or their background, and then continuous depth, which is, again, not necessarily continuous depth. It's discretized as just a much larger amount of bins, because the bins are defined by the precision of your data type, not the choice of binary, where all pixels have relative distance from a single viewpoint. We formulated probing for binary depth as a salient object detection task, which aims to segment the objects that are most distinctive to human vision. Okay, so the salient object detection, which is basically what they were doing here. In this case, the salient object is the car. So here you have salient object detection from the internal representation versus salient object detection from the actual decoded image here. So obviously the internal representation is much more useful for performing this salient object detection task than it is than this image is. Recent works have shown that vision transformers outperformed convolutional neural networks in depth estimation tasks. I guess, yeah, VITs are better than CNNs. As part of our work on depth probing, they also pursued a preliminary study where we examined the depth representation in convolutional layers, but found that they were generally weaker than those in self-attention layers. Interesting. So that's in Appendix A. So this is VIT versus convolution. Probing performance for salient object segmentation in the self-attention layers versus convolutional layers. So convolution neural networks have a bunch of increasing layers, right? And much like this picture that we saw here, right? Convolutional neural nets have the same kind of hierarchical semantic concepts, where at the lower level you have these kind of like high frequency edges, and then as you get higher and higher, you get more global kind of semantically meaningful features. So interestingly here, they're breaking down a VIT versus a CNN, and they're saying, okay, well, which one of these has these internal representations that are useful for depth earlier on? You know, it might be the case that a VIT doesn't get that depth information until much later, but let's actually see. So I guess higher is better. Convolution is this pink line, and then green is the pink is step 5 self-attention, step 15 self-attention, and then dotted is convolution. So we see that step 5, which is still early on, right? So step 5, maybe you're here, maybe it still looks like noise. And when it still looks like noise, you're looking at these dotted lines, it looks like the what am I looking at here? Pink versus green. I mean, these are pretty close. Like, it's really hard to say, but they all start lower, which kind of lets you know that at the lower layers, it's not as good. You need a couple layers just to build an internal representation that is quite good. But then the internal representation here in layer 2, kind of about the same as this. But then as you go into the decoder, you can see how it actually goes down. So the decoder, based on convolutions, right? So the dotted lines are these convolutions. The decoder, going to the very last layers of the decoder. So let's go into our VAE, right? You have your decoder. The very last layers here of the decoder actually don't have very good internal representation for depth compared to a vision transformer. The last layers in a vision transformer do seem to have a much better internal representation for depth than convnets. Right, and you kind of get a similar effect here. So mean squared error. Dice score higher is better, but mean squared error lower is better. So here you see the VIT lower RMSE than the ConvNet. Kind of useful. Maybe more proof that VITs are better than CNNs, but we kind of already knew that. Okay, synthetic dataset. John Egan, did we previously review a paper that suggested that the sampled noisy observation is not completely destroyed, i.e. pure noise? Yeah, I do remember that. There was a paper, I forget what it was called, but they basically found a bug in the implementation of diffusion models where this very last, aka pure noise, was not pure noise, and that they found that it was actually still maintaining the statistical kind of like averages of the data set. So I think the way that they found it is they found that images generated by stable diffusion were almost always kind of had a very hard time creating pure black and creating pure white. Basically, they would always tend to create this kind of gray. And why did it create that gray? Because the data set that this was trained on had some kind of average RGB value, which was this kind of like grayish color. So the pure noise wasn't quite pure noise. I do remember reading a paper on that. Okay. Let's go into the synthetic data set, though. For our probing experiments, we created a data set of synthesized images paired with their input latents. Okay, so they have some synthesized images with latents, prompts, and depth labels. Okay, so they have all of them. They have this giant paired data set of images, latents, prompts, and labels. For this synthetic data set, we generated 1,000 images using a pre-trained stable diffusion model. Okay, so they literally used a stable diffusion model to generate the synthetic data set and a linear multi-step scheduler with 15 steps. So 15 steps, 1,000 images. To ensure the quality and diversity, we sampled prompts from a partition of the Latent Aesthetics v2. Okay, so the text that they use to generate these prompts come from this Latent Aesthetics v2 dataset. The same dataset we use for fine-tuning the pre-trained stable diffusion model. Each image is generated using a different prompt and latent input. Okay. So latent input, I guess they mean what should be pure noise, but noise with different seeds. So that's probably what they're talking about there, is that when you generate this pure noise, right, you're using the random number generator on your computer to generate this, and you have to give that random number generator a seed, a random seed. So different input latents, they're probably talking about different noises created with different seeds. Since the output images do not have ground truth labels for salient object background, we instead synthesize them using an off-the-shelf salient object tracing model, Tracer. Okay. Never heard of that, but kind of a weird one. How old is this? 2022? Damn, okay. Extreme attention-guided salient object tracing network. Huh. Maybe that's worth a read. Similarly, for depth, we estimated the relative inverse depth map of output images using a pre-trained Midas model. Okay, so these are the pre-trained models that they're using for monocular depth estimation, which is depth estimation from a single image, and then salient object detection, which I guess is just creating this mask, right? So the output of a salient object detection model is a binary mask, and then the output of the Midas monocular depth estimation model is this monocular depth here, or continuous depth as they call it in this paper. Can't recognize the denoise image after training. Maybe you should train more. Maybe you should always train more. That's always the answer, is to train more. In creating this synthetic dataset, we had to address problematic images. These ranged from offensive content to images with corrupted or distorted objects. For ethical concerns, we manually scrutinized and discarded images with explicit sexual and or violent content. All right. How did you get images with explicit sexual and violent content from Latent Aesthetics v2? What? Latent Aesthetics v2? Is there weird violent content in here? Maybe a little bit. Yeah, if it's like weird movie stills, like there's probably movie stills of like violence. Okay. We took out images with the depth concept such as black and white comic art. Okay, so no, only natural images. After generating the images, we removed images where tracer failed to identify any salient object. The resulting dataset has 617 samples. Okay, so they kind of filtered out anything that would be a little bit weird. They want just only natural images where there's an obvious concept of depth. Split it into a training and test set. It's kind of a hardcore split there. You have more tests than you have train, which is unusual, but they're doing unusual things here, right? They're kind of dissecting the frog, so... LDM appreciate it because they give a table that train 100 epochs is the efficiency of DDIM train 1,000 epochs. Yeah, generally any technique that does things faster is just going to be worse in other ways. So I'm sure whenever they sold DDIM versus DDPM, they were like, oh, DDIM is so much faster. You don't have to take every step. You can skip steps, but you don't get anything for free. And what it sounds like is basically that DDIM doesn't produce the quality that you get with DDPM. To investigate discrete binary depth representations inside the LDM, we extract the intermediate output, epsilon theta LT R HL by WL by C. So L here is the specific layer, right? So you're going to have a bunch of these self-attention layers in a VIT. In a convolutional neural net, you'd have a bunch of these convolutional layers at a specific sampling step t. So the sampling step t is just how far along this process you are, right? But it's a little bit non-intuitive because you're adding noise when you're training. So time step 0 is actually the end. So when you're doing diffusion and generating an image from noise, you're actually going backwards in time from the perspective of the diffusion model, right? The diffusion model thinks that it's actually predicting the noise which you're adding, but you're actually removing noise. So that's the sampling step. Here you have some theta is actually probably the model, some layer, some time, and you're taking the basically the intermediate representation there, which is just you're cutting the neural net and then you're just taking the values at that particular layer. A linear classifier PB, which means they're just adding a little linear classification head on top of that, is trained on these output representation or these representations to predict pixel level logits. This. So the pixel level logits end up giving you basically the probability that it's either basically 1 or 0, because in this case it's binary depth, right? And then you basically just take the argmax there and say, okay, well, my classifier says that this pixel here is more likely to be a 0, and this one here is more likely to be a 1, and this one here is more likely to be a 0, and then you do that for every single pixel in the image, and you basically get this binary depth. And there you go, 512 by 512 is the image size for salient and background classes. This probing classifier can be rewritten as this. Okay, so you take your weights. Here, this W is the linear classifier, so your extra little model head W here. You're using the representation that's coming out of your LDM here, your intermediate representation. You are interpolating, I guess, for some smaller latent height and width, right? The latent's going to be a little bit smaller. The latent here, where is it? Right here. Nope, up here. See how the latent is smaller by some factor m. So you kind of have to undo that to get the actual full-size image again. The full-size image is 512 by 512. And then you're taking the softmax to turn those logits into 0 to 1, which are then going to be the binary background, foreground. The LDM's self-attention layers operate at different spatial and feature dimensions. We interpolate lower resolution predictions to the size of the synthesized image. This is the interpolation here. Interpolate. They're just making it bigger. Lots of different types of interpolation. You know, you have bicubic interpolation, and generally the making an image bigger, the interpolation is also a kind of a time accuracy trade-off where there's faster ways of interpolating, and then there's cheaper, faster, but worse ways of interpolating and resizing an image like that. Or there's, let me just do this, image interpolation, image resizing, scikit. Yeah, here we go. Resize, rescale, and downscale. Let's actually go to the resize here, resize function. And if you go here into the resize function, you can actually pick the algorithm that's used. Where is it? This one, preserve, anti-aliasing sigma, order, resized. Alright, maybe I'm not going to be able to find this. I'm all over the place today, guys. I apologize it. Okay, but they're resizing these latents so that they get a 512 by 512 and they can compare it to the actual ground truth depth. W in R C by 2. So this is the actual little final linear head that they're using, that they're training for this classifier, your probing classifier. W is updated using gradient descent that minimizes the cross entropy loss, which is just your standard classification loss between the ground truth depth and the predicted depth. So this is the predicted depth, this is the ground truth depth. And the ground truth depth, they're somehow just magically getting. Right? We generated 1,000 images using a stable diffusion model, and somehow you have the depth for that, which is a little bit weird. I don't know how they got this ground truth depth label. We measure the segmentation performance using the dice coefficient between the predictions. Here you take the argmax. So what's coming out of here, this is the logit, and then you're feeding that logit into the softmax. The logit is a negative infinity to infinity. Then you're feeding it through the softmax. It becomes a 0 to 1, which you can interpret as a probability, and then you take the argmax of that. So the reason this is two-dimensional here is because basically you're classifying this, so you're classifying each pixel into two possible classes, either the object class or foreground, and then background. So let's say you classified a pixel and you got a score of 0.99 for the first dimension, which is the object, and you got a score of like 0.1 for the background. That's telling you it's a 99% chance this is the foreground, 10% chance is the background. So in order to choose one of those, I'm going to argmax. I'm just going to pick the one that's the bigger one, and that's going to tell me, okay, this is probably foreground. So D tilde versus D hat or D caret. This is actually a single number. DB is two numbers. And the synthetic ground truth, DB. I still don't know how they're getting this. If you're generating these with stable diffusion, how the fuck are you getting a synthetic ground truth for that? And then here is the actual dice loss. So basically the total number divided by the overlap. Continuous relative depth information. We are also interested in a more fine-grained depth S dimension, also exists in the LDM. We extract the output from the self-attention layers and use a linear regressor on them to predict the Midas relative depth map. Okay, so now it's not going to be a classifier. They're going to do the same thing where they cut the neural network and then they use that intermediate representation to train a new model, but in this case they're not going to be training a classification model with a cross-entropy loss and 2 categories where you have background and foreground, you're instead going to be training a regression model. And the regression model just outputs the value directly, right? So in a classification model, you're outputting this logit, and then you're putting that logit through the softmax and pretending that that's a probability, and then using that probability to pick the right class with an argmax. But in a regression model, the model itself just outputs the number directly, right? So here, that's why this is the last dimension here is 1, because it's just outputting that number directly. So you have 512 by 512, still the same image map. This is the Midas relative depth map. I don't like how they just keep changing the terminology here. This is what they're calling the continuous depth map before. Now they're calling it the relative depth map. But it's basically the same thing here. You see these 512, 512. You have your single little linear layer here. You have your specific intermediate representation at some layer L at some time step T, and you're interpolating that to make it 512 by 512 just so you can interpret that. You update this little depth prober. What should we call this? If this is a linear classification probe, I guess this is a linear regression probe, but they're using a Huber loss between the ground truth depth and the predicted depth. Again, I still don't know how the fuck they're getting these ground truth depths. Also experimented with regularizing depth predictions as with a smoothness constraint. Okay, so adding an additional loss there in addition to the Huber loss, but I guess they didn't get good results on it. This is the original paper where they used that extra regularization. However, the smoothness constraint has a negative impact on probing. Yeah, I think if you're trying to just determine the quality of this internal representation, you don't want to get too fancy with your classifier, your probing classifier, and your probing regression model, right? You kind of want to see if just a very simple classifier can find something there. If you're adding all these extra losses, then you're not really measuring the quality of that intermediate representation anymore. Following existing practices, the accuracy of depth probing is measured using root mean squared error. So this is just, you take the error, you square it, and you take the average mean, and then you take the root of that to get rid of that square. We probe the internal representation of the salient regions in depth across all the self-attention layers. So layers all the way 1 to 16. Of each of the latent diffusion models at sampling steps, probing classifiers were trained separately on each layer and step. This is what you want in these kind of scientific inquiry papers, is that they go deep, right? They take this little frog brain and then they dissect the little frog brain. They spread all the neurons out on a little petri dish, and they have their little probes, and they're like putting one probe, and they're like, okay, well, let's put the probe here at the beginning, and then here in the middle, and then here at the end, and then here. So they're like probing every single little part of this little dissected frog brain. We fix the number of training epochs, optimization algorithm, and learning rate. Yep, if you're doing these kind of experiments, you don't want to try over a huge amount of hyperparameters. You want to basically keep as many other things fixed so that you can separate out the causality and the correlation of the variables that you do care about. Mr. Z dropping some knowledge here. DDIM is a sampling algo which should be independent of the training phase. Yes, training 1,000 epochs definitely helps improve. Using the sampling algo like DDIM can help you fully reach that generative ability with less sampling steps. Yes, that's another thing that we saw. And then we should expect similar results with DDIM sampling and DDPM given the same well-trained model. And more steps. So DDIM is DDPM if you use the same amount of steps. Is that correct? Let's see. Are DDIM and DDPM effectively equivalent given the same number of sampling steps? I think they're not going to be 100% equivalent because you don't have that noise, but even if the number of sampling steps is the same, because the DDIM has the noise and the DDPM, or the DDPM has the noise and the DDIM does not. Yeah, adding noise. Alternative sampling technique. DDIM can generate images faster than traditional, produces samples in fewer steps. Samples tend to be of comparable quality. Ooh, I don't know about comparable. Yields more diverse output since it pulls from different points in the diffusion trajectory. While the core denoising and the underlying model might be the same, the sampling strategies differ. DDIM's ability to sample from multiple points can lead to faster and potentially more diverse sampling than the traditional DDPM. In practice, if you're using the same number of sampling steps, DDIM might produce more diverse or different samples compared to DDPM. Okay, so even if you're using the same number of sampling steps, you're going to get slightly more diversity from DDIM, which is weird because DDPM is the one that has noise. Okay. Controlled probing experiment. Because of the large feature space of LDM, probing classifiers may find a spurious representation of depth. We need to find a baseline to quantify the strength of an internal representation. For both, we measure the baseline using probing classifiers trained on the internal representations of a randomized LDM. And randomized here just means that when you initialize the weights of a latent diffusion model before you even train it, right? You can do the same thing. Before you even train it, you just initialize all the values for these neurons, you cut it, and then you just use that. And that's a pretty good baseline. I do agree with this choice. That's a very clever choice. Linear representations of depth and salient objects. For both probing tasks, we obtain high probing performance using the internal representations, especially in the later denoising steps. So once you're closer to that actual final image. The performance increased significantly in the first 5 steps and gradually converged in the late denoising process. In the last step, probing classifiers achieved the average dice coefficient. This is basically the plot that we were looking at here. Salient, as figure shows, probing classifier captured salient objects while inferring on a decoder side self-attention output at the last denoising step. Even though the spatial dimension of the input representation is only 1/16, so we get the actual number here. So here they have to interpolate to make the latent 512, and we know that that relative ratio between the latent height and width and the real image height and width is 1/16. So that's that number. The predicted masks still catch fine-grained details such as limbs. Our synthetic data includes a variety of objects, including humans, blah, blah, blah. It's unlikely the linear classifiers learn to select features corresponding to certain kinds of objects or memorize their locations in images. Yeah, but you can see why it's important, right? Why would it be important for a diffusion model to get an idea of human legs and limbs and chairs very early on in the diffusion process? And one way to think about it is that the texture is going to change, right? So like the texture of this dog's fur versus compared to the texture of this background are completely different things, right? So the sooner you can make that decision of this is going to be dog texture versus this is going to be background floor texture, the more time you're going to have in this diffusion process to actually create that dog's texture and actually create that background texture. So it would make sense that there's kind of like a pressure. There's pressure being applied to this diffusion model during its training to make that decision earlier in this denoising process, right? Where it's very early on in this process, it's trying to come to that decision of like, okay, this is going to be background, this is going to be dog, this is going to be the human arm, this is going to be the foot, and so on, because I think it needs those extra steps to actually create the texture. So that's kind of my reading of the bones as to why it even happens to have these pretty high-level semantic features like legs and chairs that exist in these internal representations really early on in the denoising process. Probing classifiers also obtain accurate depth estimations at later denoising steps. Yeah, but the accurate depth estimations at later denoising steps is less impressive to me because at that point you're kind of already looking at a picture of the thing, right? It's like later on in here, for example, in a ConvNet, it makes sense that there's kind of like an eyeball looking feature, right? But if you find eyeball features at the beginning, that's a little weird, and that's kind of what we're finding here. In the controlled experiment, the probing classifiers performed significantly worse when trained on the randomized LDM. That's good. That basically means that they are correct. Their baseline is shit, so shows that their technique that they're using now is good. The highest dice coefficient achieved was only 0.3, and the smallest RMSE was 0.95. The substantial differences indicate the internal representations of trained LDMs have a strong correlation with the depth, which cannot be easily captured by a random model. So they're not just imagining it. There is some kind of strong, there is an internal representation in the layers of this LDM, this vision transformer in the LDM, that correlates very strongly with depth. So, which means that this LDM, even in the very early layers, has some notion of depth. And you can tell the difference between the layers and the quality. So here, RMSE, lower is better, right? So here you have all the different steps. So at step 1, which is the red, the very first step, you can see how it gets better and better and better and better. It's kind of interesting here. Look at this. So you have the encoder layers, and then you have the decoder layers. And actually here, the bottleneck is the actual latent itself, right? The bottleneck is the representation here, right? This is the actual thing that's getting diffused and removed noise, added noise. So it's kind of interesting that there's kind of this spike here where the representation, the latent itself, which is the representation in the bottleneck, actually has this spike for the root mean squared error. The layer right before it has a better internal representation of depth, and then the layer right after it in the decoder has a better representation of depth. And here, the dotted line is the random. So if you were just to take the randomly initialized values for encoder 2 layer 1 and then try to predict depth off that, this is what you would get. So it's good that this dotted line is up here. But this is also kind of cool to think about if you look at this, right? Look at this. The dice score actually kind of goes up as you go through this decoder. So a randomly initialized decoder vision transformer where the weights are just literally random shit has some notion of depth which is built over those layers, right? That's kind of a crazy thing. The fact that this isn't just like a pure straight line or just like a little fuzzy line over here by 0. The fact that there's just kind of a little tiny bit of an upward tick. That's some magic right there. Okay, probing performance of salient object segmentation and depth segmentation. Performance grew rapidly in the early denoising process and converged after step 5. So they're saying kind of once you get to this orange line, you kind of end up in the same place. So these lines very quickly kind of converge. You see the difference between these is bigger than the difference between these. Row 2 shows the prediction of 2 probing classifiers. The probing classifiers achieved an average dice score of 0.85. Probing prediction, synthetic ground truth. Okay, so you have a generated image. Here's the actual ground truth, and then here is the per pixel classification of this probing classifier model that is only looking at the internal representation. And you can see how it pretty much has most of it. You can see it has a notion of the wings and the beak, all the different parts, the human, the leg, the space in between the legs. Like, that's even more crazy, right? It's not just like a uniform blob. It's like this actually has like a hole here for the legs. Here you have the same thing but with the depth. Pretty good. I'm just looking here at the depth, right? There's kind of interesting how it's imagining that there's a depth to this background here, and even this ground truth depth for this bird actually is a little weird. Like, what is this? Right? Like, why does the sky have a depth to it? Should it? I don't think it should. This isn't real ground truth depth, is it? And here, these are windows, right? So all of these should be at the same depth. But the top here is not. See that? Here the top isn't. Top corner, that should be the same as depth. So the ground truth depth isn't even 100% correct. But the more impressive thing here is the reconstructed depth. Pretty cool. Depth emerges at early denoising steps. We saw a dramatic increase in probing performance during the first 5 steps. For both probing tasks, the performance difference between successive denoising steps vanished after step 5. High probing performance at the early steps suggests an interesting behavior of latent diffusion models. The depth dimension develops at a stage when the decoded image still appears extremely noisy to a human. Yeah, this is the entire paper is basically this. The images decoded at early denoising steps are heavily corrupted. Human viewer can barely capture any meaningful information, but the LDM representation does have a very clear idea of what's going on there. Continuous depth estimation also appears at the earlier steps. We ran Midas on the partially denoised images, but it failed to find a significant amount of noise that was removed. So what they're talking about here with this tracer model and this Midas model, these are kind of basically like baselines, right? They're saying, okay, well, if you take this here, it might not look like anything to us, but to something like Midas, which is a monocular depth model, which has been trained on some data set, maybe it can pick up something there, and it can't. You know, that's what they're showing you here, is that the Midas can't pick up shit, but their little tiny classifier, or not classifier, in this case, a little tiny regression model that just uses that internal representation, it can pick up something. Is depth represented in latent space? Because LDM operates on a latent space representation of an image, one might ask whether this representation itself contains depth information. To address this question, we performed a probing study of the VAE self-attention layer. The self-attention layer in the VAE cannot decode salient objects from the corrupted latents at early steps. So the VAE cannot decode salient objects from the corrupted latents at early steps. So if you just take these latents at the very early steps, it's hard to see here, but right, this is in image space, but you can imagine that there's a latent space, and if you took this latent space that started with pure noise and you removed one step of noise and then fed it back through the VAE, it would still look like noise, is basically what they're saying. Its performance starts to improve when details in latent vectors become more perceptible. After the latent is completely denoised, the segmentation performance of VAE self-attention is slightly lower than the average performance of the LDM decoder side self-attention. For the depth estimation, the self-attention layer of the VAE failed across all steps. All right. So what are we seeing here? Weak depth information was found in the VAE's bottleneck activations. Right, so this is they're talking about how there's this kind of spike here in the bottleneck of the VAE here, which is kind of weird, right? Why is that there? But the LDM encodes a much stronger representation of depth. This table shows the probing performance achieved by LDMs and VAE's self-attention layers at steps 5 and 15. So you have the diffusion model, which is the one that's actually adding and removing the noise, and then you have the VAE, which is just the one that the one that actually takes the image in image space, compresses it down to that latent space, and then the diffusion model is actually doing the per step removal. But we can see here how the latent diffusion model is the one that has the depth representation. Right? The VAE, they did the same thing where you cut the VAE and you look at that intermediate representation and you're just not able to detect an object or able to detect the depth in the same way that you would inside this latent model. So it's telling you that it's not the VAE that built the depth representation, because that would have kind of been an obvious conclusion, is that, okay, you have some notion of depth in these latent diffusion models, but that notion of depth is just coming from this VAE, right? This VAE has been trained to reconstruct these images, therefore it has built over time this kind of internal depth representation, and when the LDM is adding and removing noises, it's paying attention to what's inside that VAE latent, and that VAE latent has some kind of depth information in there. But here they're telling you, no, it's actually the diffusion model that has the notion of the internal representation that has depth in it, not the VAE. even though it's a little bit, right? So the latent diffusion model has it very early on, but at step 15, the VAE does have it, right? Because now you actually have, the image actually looks like something, right? So once the image actually looks like this, you could go into that VAE, you could take this image, encode it, and then decode it, and inside that VAE, when you're encoding and decoding it, you do have some notion of depth. But if you were to take this image, encode it, and decode it, there'd be no notion of depth in there, which is what they're showing you here. RMSE. RMSE is root mean squared error. It's the way that they're judging the continuous depth. So when you're training a model to regress values, right, it's predicting the value directly. So you can't say, you can just say, okay, well, it predicted a depth value of 0.5 and the real depth value is 0.4. I'm going to take the difference between those, square them, and then average it over all the pixels, and that's the root mean squared error, RMSE. Okay, and now let's look at figure 4 here. LDM's internal representations of salient objects and depth appearing surprisingly early in the denoising. Probing the internal representations of VAE, however, cannot find the salient objects and depths when latents are corrupted. Okay, so they start with this prompt here, Lapierre Pulsum 600 FDJ road bike. Kind of a weird prompt, but sure. Okay, at step 1, it's basically noise, right? But you're starting from latent noise, and then you're taking that latent noise, putting it through the VAE decoder, and getting this image here. Tracer synthetic label, so I guess here they're just showing you that this tracer model can't get the foreground background. Input latent 4 channels, 2 by 2. So I guess here they're showing you what each of the 4 channels of this latent is. So you can see how there's 4 bikes, I guess. But the important thing to look at here is that the VAE dice score, which is basically how good is that internal representation in the VAE at predicting depth, you can see that it's basically garbage at step 1, and it stays mostly garbage, and then only at the very final steps, right, step 11 and step 15, only when the image has started to emerge do you start to get higher dice scores. But for the latent diffusion model, it actually has a pretty good idea about what's foreground and what's background right at the beginning. And that's the crazy part, is that this latent diffusion model has already made up its mind. So even though it doesn't look like there's anything going on here in these early diffusion steps, it's already decided there's going to be a bike right here, and there's going to be a wheel right here, and there's going to be this this little, whatever those are called, joists. I don't know. What are the center parts of a bike called? The stem? The axle? No, the axle is over the wheel, but okay. And here, that's the binary depth foreground, and this is the continuous depth. So regression. And here the regression is color coded from red to blue just to make it look nicer, but it's a single value. It's just a single number. And you can see the same kind of thing, right? RMSE stays very high for the VAE the whole time, all the steps. But then as soon as once you're looking at the LDM, it actually goes down more consistently. And you can see it already has a pretty good idea of, like, it might not know the like placement of things, so it doesn't know exactly, like, there's going to be a chair here and there's going to be a thing here, but it's already kind of decided what the vanishing horizon point is. It's basically saying, okay, there's going to be windows here, and it's going to be kind of facing that direction. You're going to have something closer here and something farther away, versus this Midas model here. You see how it's kind of nonsense up until the very end. Okay. Causal role of depth representation. Probing experiments show a high correlation between the internal representations of LDMs and the depth of his output image. But does this representation play a causal role? It kind of has to, right? Like any intermediate representation is in a sense causing the next layer to activate in a certain way, which then causes the next layer to activate in a certain way. So I think they're kind of playing with the definition of causality here, but like, it's for sure it is, you know. We designed causal intervention experiments for salient and object and depth representations. We want to change the model's output by solely modifying the internal representations in the LDM. So they're going to basically go here into these representations here. Obviously, this is the output of the probe, but they're going to mess with it and see if they can get it to change. So they're going to go into the latent diffusion model at step number 4 and fuck with this bike and see if it actually changes the way that the bike finally looks at the very end. Repositioning foreground. Our goal is to see if changing the depth representation with the same prompt and initial input will lead to the corresponding change in apparent depth in the output image. To modify the geometry while preserving the semantics, we test a minimal change. We identify a foreground, translate its representation in 2D space. Okay, so they're just going to basically shift it. When translating the object, we use a modified salient object mask d'B. So dB is the original mask, and then d'B is the shifted. I think they're probably just going to, like, I don't know, we'll see what they do, but they probably just shift it like that. Randomly translating with vertical and horizontal translations sampled from a uniform distribution, -120, -90, 90, 120. I think this is in pixel space, so more so shifting it XY than shifting it up and down, or X-axis than up-axis. We created 5 different d'B for each sample in the test set. The intervention then modifies LDM's representation so the probing classifier's output, if using a modified representation, changes to D'. This is achieved by updating the internal representation using gradients from the probing classifier. Okay, so here you have your cross-entropy loss, right? Because they're doing this for the binary classifier, PB. So you have your binary classifier, PB, which is predicting dB out of these intermediate representation. You have your cross-entropy loss between that dB that's predicted and the d'B, which is the changed, the modified salient object mask, d'B. And this is going to be weird because you basically have like kind of like a shifted thing, and then you're going to push the intermediate representation in the direction of that gradient. So you see here how they're taking the gradient here, G, is the partial derivative. That's what these fancy backward D's are. The partial derivative of that loss with respect to this intermediate representation, and then they're going to adjust it by that. The weights of PB are frozen. E theta is updated using atom with gradient calculated by equation 3. Okay. So do we have a pic of what that's going to look like? Here we go. This figure illustrates our intervention workflow where the foreground object was repositioned in the intervened output. Okay, so here you have the original one. So here's the original dB, the original predicted foreground, background, binary depth from your probing classifier. Here's your probing classifier. It's taking in your intermediate representation. Your intermediate representation, here it is. It's coming from the decoder. So here you have your latents that are starting from pure noise. You're feeding your pure noise latents into the latent diffusion model. This is the actual diffusion model, right? You're looking at this part here. You're taking out that intermediate representation. You're feeding that into your probing classifier. Your probing classifier is giving you the depth, and as we learned, we know that even at time step equals 1, the latent diffusion model already has a pretty good idea about where the flower is going to be and what the background is going to be. And that's ultimately if you were to remove noise up until time step t, which is where your final image is, and then you feed that final latent into your variational autoencoder, your VAE, which will take that latent, which looks kind of like this, and it'll turn it back into image space, and that's where you get this image here. This is actually a really nice figure. I really like this. The color coding here, very clean. Original, modified, affected. Okay, so this is the original flow. Now here they're going to be doing the modified flow, right? So they're going to take the same latent, the same starting noise with the same random seed. They're going to feed it through the latent diffusion model, right? The latent diffusion model is going to try to predict that noise to remove that noise, and they're going to take the intermediate representation, and instead now they're going to say, okay, well, we're going to take this intermediate we're going to take the final output of our probing classifier that we did it normally, and we're going to translate it, we're going to randomly shift it, and then we're going to push, we're going to figure out what the gradient of this random shift is with respect to this intermediate representation, which is what they were doing here, and then we're going to just change the intermediate representation by that. So we're going to go in, and we're sitting there with this dissected frog brain in front of us, and we're like sitting there probing it with these little metal probes, and we notice that it's activating at this. We're going to change that activation and then change it. So then whenever it propagates through the rest of the little frog brain here, it's now different. So you've messed it. You've messed with it, right? You've changed the signal, and you can see how now, because it's modified, this one is now affected. You see this affected, modified, and boom, boom, boom. And it goes all the way, all the way, all the way, all the way. And now when you take that final latent at time step t, you've removed all the noise, and you feed it through the decoder of your VAE in order to get your final image. Now this image looks a hell of a lot like this, right? So by doing this entire thing here, what they've shown is that it's causal, right? It's causal. If you change the depth representation, or our idea of the depth inside the internal representation of the decoder part of the latent diffusion model, it will change the final output of the diffusion model in image space in a way that kind of matches up perfectly with this. So you see that? It's like, it's kind of hallucinated other things around it. You know, it's kind of changed the composition of the whole thing because of it, but you can see how the original shape is still there. ControlNet, yeah, this is kind of very similar to ControlNet, right? And ControlNet is this, you're kind of doing similar thing where you're basically using skeleton poses or canny edge maps or something like that, segmentation maps, and then using that to condition the diffusion model. So it's similar in that you're introducing that information here, but is ControlNet conditioning, or is ControlNet? Is it conditioning, or is it like more so directly adding? Yeah, I think it's not actually conditioning. It's like literally adding to it. So you're training this extra little part here. So you could think of it as having this like little extra little module here, and then you're sending a conditioning into that little extra module, which is then modifying the internal representation. So yes, in a way, this is basically exactly ControlNet. You're modifying the internal representations, except in ControlNet, you're learning you're learning this little module here that actually physically adds to the representation. But here you're taking the gradient from a probe, from a classification probe model, and using that to adjust the internal representation. But at the end of the day, it's the same thing, right? You're taking the values that are coming out of one layer, and in ControlNet, you're just adding the values from this little ControlNet part, which is itself conditioned on edge map or something like that, like maybe something like this. You know, this is a canny edge map. And it's also, ControlNet is more pervasive, right? It seems like they basically, you have parts of it going in at multiple places. You see here, it's going in at multiple layers, versus here, it's only going in at one layer. Yeah. So that's a good observation, Yujun, is basically ControlNet. Sigma theta is updated to the probing classifier's prediction changes to match the modified label. We replace sigma prime with the original activations and resume the denoising process. Since LDMs use the latents denoise from the previous step, the activations after the intervened layers are also affected. Okay, intervention on saliency representation, intervention on depth representation. Null versus intervened. What do they mean here? Quantitative show that intervening had causal effects on the model's output. Yeah, I mean, we can just see that clearly here, right? I don't think we need to plot whatever the count of interventions is. The median RMSE between modified depth maps and depth maps of 10855 intervened outputs is 0.63. Okay, so somehow these plots are basically just showing you that these are different, but I think this is much clearer. Original image, intervened image. And here they have basically the same thing, but it's going to be nicer here. Models original outputs and labels for salient objects or depth. Column 3, the modified labels used in intervention. Column 4. So here you have the original output, the original label, the modified label, which is now shifted, the intervened output, and they're kind of showing you the highlight to show you that the original kind of salient object, as they describe it, now lines up with the modified label. This one does not, actually. That's kind of interesting. Look at this. So here they have like a bust of this person's face, and then they shift it upwards, and it doesn't just shift it like these people. So this one is actually a very nice example, but this one's a little bit weird. It actually ends up creating kind of like a shadow of the bust. Huh. That's great. You know, I love to see like failure cases like this. Same thing here. Look at that. It doesn't quite shift the bird. It kind of like makes the bird almost appear in a different angle. Huh. That's kind of interesting. Super interesting. Okay, and what do we have here? Here we have the same thing, but for the depth, or the continuous depth. Original label, modified label, intervened output. Interesting. It's kind of just gotten rid of the background here, these skyscrapers. Here it's also drastically changed. Very, very interesting stuff to look at. To assess the effects, we computed the dice coefficient between the modified mask and synthetic mask. If the saliency has a causal role, the salient regions of the newly generated images should match the modified masks. We performed a similar intervention on the continuous depth representation. Okay, so basically the same thing. They're going to be modifying this depth map by shifting it, calculate the gradients using the same way, except instead of using the cross entropy loss, now they're using this Huber loss. Intervene on all self-attention layers in the first 3 sampling steps. Okay, so maybe this is more similar to ControlNet than I thought. I thought they were intervening only on a single layer, but it sounds like they're intervening on all the layers. So that's kind of more similar to what ControlNet is doing, where it's intervening at every single layer. You see, this is ControlNet. We conducted our proposed intervention on the test set of our synthetic datasets. The resultant 1,855. This is like weird. Like, I don't like this. Like why do you keep telling me these numbers? Like, just put these numbers in a table, and then just show me the text should be kind of like conversational, and then put all these like numbers in a table, which they did. But they're also just, they keep putting these numbers in the text, which makes this kind of annoying to read. Successfully reposition the foreground objects by solely modifying the self-attention activation using the projection learned from the probing classifiers. The median RMSE for the outputs is that. Null interventions is that. We created an additional salient object in the middle of the scene by inserting the object's depth map with increased depth value. Okay, I don't know. They don't really mention the fact that it doesn't actually perfectly work every time, though. The fact that it, like, makes us like, why is it kind of ignoring it in some ways? Okay. Related works. Finally, we get to related works. That mouse is thick. Yeah. I use the big mouse because I want people to see my mouse, because like I often like hover on things and point at things and figures. So I figured if I'm gonna do that and I'm gonna be like kind of hovering and pointing at things, I have to have a big mouse. So that's why I'm living the big mouse life. It's actually incredibly annoying, like even for like for anything. Like it's hard to know exactly where my mouse cursor is a lot of times. A sequence of moving motorbike created by intervening on the LDM's internal representation of a salient object. Okay, so here you have the original. We see that we're shifting, and you're getting slightly different things there. This is kind of weird. Like, why does it hallucinate like a logo in the corner here on these ones? Right, and another thing to look at here that I'm noticing is that the appearance of the background change, right? Like the texture changes. So it's not like, you know, it's like generating new grass texture every time, but every single one of these should come from the same seed. So it's a little weird that given the same seed, you shift this internal representation and you get different appearance of the final kind of texture and coloration. I mean, it makes sense, but it's still kind of weird, right? It shows you that it's not like there's a lot of deeper things going on there, right? The latent diffusion model has like, it's doing all kinds of weird stuff, and even just the relative placement of this bike impacts what it's going to do in the background. Right, like if you look at the original data set that this latent diffusion model was trained on, maybe most of the pictures where the bike is in the foreground like this have trees, versus most of the pictures where the bike is clipped are stationary, and therefore that's why you get this like kind of rock texture. I don't know. I'm always like curious as to what aspects of the core dataset distribution are driving these weird behaviors in the final model. Because that's kind of my point of view, is that anything that the neural network is doing is coming from something in the data set, and it's on you to just discover what that something is. Holy heck, an afternoon Hoopo stream. Yeah, maybe I'll talk about it later, but I'm probably going to actually change my streaming times. I'll post more information on the Discord, but I'm probably going to start streaming on Saturday and Sunday mornings on my end. So hopefully it doesn't just collapse the community. You know, I know that some of you people, the reason you watch these streams is because I happen to stream at a weird time. So if I change the time, I might lose a bunch of you, you know, and that's kind of sad to think about. But I do need to change the time that I stream to probably Saturday, Sunday is what I'm thinking. I'll be able to catch more. All right, that's good. That's good. Okay, so here they're going to be talking about other people that have also been probing into stable diffusion and so on. Work of Kim, performed contemporaneously and independently, touches on some of the same issues but from a different perspective, generating geometrically plausible images. They found a nonlinear depth representation inside a pre-trained 2D DDPM using multi-layer perceptrons. Okay, that's very similar to what they did here, except multi-layer. Here they just used one layer. The results also indicate that the depth dimension emerges in the early denoising. Our probing experiments, however, suggest that the 2D LDM has an even simpler linear depth representation. Right, so linear depth representation versus multi-layer perceptron. So they're referring to the fact that their little probing classifier and probing regression model are just linear, right? And what that really means is that there's just one W here, right? So it's not like there's a multi-layer perceptron or a multi-layer neural net that consumes this internal representation, but it's just like one layer, one W. Okay. Kim approximated the pseudo-ground truth of depth using predictions from aggregated representations of multiple feature blocks. They compared the pseudo-depth label against a weaker prediction from a single feature block. This difference is applied as a guidance to improve the geometric consistency. Okay, so this was apparently some other paper where they did something like that. From an interpretability, we seek evidence for a causal relationship between internal representations and depth. Yeah, I think they proved that beyond a shadow of a doubt. Our intervention on depth representations can control the scene geometry with respect to a predefined label. I think the use of the word control there is a reference to ControlNet. Extrapolated the intermediate activations of a pre-trained diffusion model for a semantic segmentation. Reveals that the diffusion model encodes rich semantic representations. Our work shows that the internal also captures geometric properties. Utilize features to optimize the neural radiance field for 3D synthesis. In contrast, our study centered on finding and interpreting the 3D representations inside an LDM. Okay. Conclusion. Our experiments encode evidence that the stable diffusion model, although trained solely on two-dimensional images, contains an internal linear representation related to scene geometry. Probing and uncovers a salient object background distinction as well as information related to relative depth. And I think these are more similar than they are different. Again, I see what they call relative depth or continuous depth is just depth, but discretized at a more finer detail. And then foreground background distinction or a mask is essentially a more is also discretized depth, except now you're discretizing it into 2 bins rather than 256 bins if you have a uint 8 depth. Furthermore, interventional experiments support a causal link between the internal representation and the final image. So if you fuck with the internal representation, you get a different final image. These results add nuance onto the ongoing debates about whether generative models can learn more than just surface statistics. And I think it does. It shows that there is some pretty interesting representations that it's learning. Our experiments also suggest a number of avenues and natural extensions to look for representations of other scene attributes, such as lighting or texture. That could be cool. Instead, just as certain language models are set to rediscover the NLP pipeline, perhaps LDMs recapitulate standard steps in computer graphics. More generally, one might look for models of semantic aspects of a scene, such as sentiment. There you go. Sentiment analysis is all you need. Okay, let's scroll down here to the appendices. I looked at my phone clock and realized it was just about 11. My computer clock is, and I just went with it. Weekends is better for you guys. I used to watch your stream at this time. Yeah, I'm a little sad, but I think it should. I just have personal family reasons why I can't really stream at this time anymore in the future, so that's why I'm moving to Saturday, Sundays. I also think that there's more people. Like, I was looking on the internet, and it seems like more people stream on Saturday, Sundays. So it's kind of like a potential, you know what I'm saying? There's more people streaming, so you're competing with more people, but then there's also a lot more people watching on Saturdays and Sundays. So it's like, maybe it cancels out. I don't know. I don't know how many other machine learning streamers there are, to be honest. We found stronger depth and salient object representations, the activation of self-attention. This is the one that we already saw, right? Where the convolutional based versus VIT based, right? VIT, vision transformer, also called VITs. You know, some people call it a VIT. I call it a VIT. But the VIT has a much stronger kind of depth representation even at the final layers of the decoder compared to the CNN. And then the other interesting pattern I saw here was the fact that right in the bottleneck, you get this spike downwards, or this spike upwards in RMSE, which is, I think, kind of interesting. Spatial and feature dimensions. So here's the actual size. So 64 by 64 down to 32, then down to 16, then down to the bottleneck, which is 8 by 8. Obviously, for example, I think a good example, let's go to VAE, this one. So in some of these pictures of a VAE, they show you, yeah, here, this is the one that I want. So this is a convolutional neural net VAE, but the important thing that I want to show here is that your input is a three-dimensional image, right? So you see that 3, that's the number of channels. And as you go higher up in this hierarchy, the size of the image might be getting smaller. So you see the height and width might get smaller, but the actual number of channels, sometimes also called feature dimensions, increases. So you see that. So it's a smaller image, but each pixel, or like each height width slice of that now has more dimensionality to it. So it has more space to encode semantic information, right? So that's kind of what's going on here, right? Where initially it's 64 by 64 by 320. That's the actual latent. But then in this latent diffusion model, when you're actually ultimately getting the noise, you compress it into this bottleneck that's 8 by 8, but 1280 deep, right? So here you go. That's the depth right there. In this case, it's 1024, but it's 8 by 8 by 1280 in the middle of that bottleneck. Here we have another picture, kind of similar to what we saw before. Choices of intervened denoising steps. So when did you intervene? Right here they intervened at the very first step, but here now they're showing you what if you intervene at later steps. So if you intervene in the first 3 steps, right? So here's the original label, and then you're shifting it. So now you shift it. If you intervene early, it kind of just creates the, I don't know what the fuck. I don't actually, to be honest, I don't even know what I'm interpreting here. Like, it just kind of looks like the same shit. Maybe there's something weird here where it puts it on stilts, versus when you intervene later, it kind of fills it in with pillars. I don't know exactly what I'm supposed to be seeing there. Here, if you intervene early, it kind of makes more sense, maybe? I don't know. And if you intervene later, kind of makes less sense. I don't know. Those kind of look about the same. It doesn't really seem like there's a huge difference between intervening early and intervening late. Same depth, increasing depth. Interesting. So here they change the depth between these, I guess. And at some point it just decides to just disappear, the thing. Similar kind of thing happening here, where at some point, if you make the internal depth representation, if you make that object in the internal depth representation far enough away, the latent diffusion model says, well, there's just nothing there, and it just zeroes it out. This is the part that they were saying where if they try to add this extra smoothness regularization to the probing regression model that is predicting the continuous depth, then they said it did not improve things, which is why they got rid of it. But here they're going to actually show you. The smoothness constraint negatively affects the performance of the probing regressors. So the probing regression model is worse at creating the creating the depth image from the internal representation. That's what the negatively affects the performance is, especially when the resolution of the probing prediction is low. The resolution of the probing prediction is equal to the spatial size of the input activations, which can be as small as 8 by 8. Oh shit, okay, that makes more sense. So why do we see, back here, why do we see a spike in the bottleneck? Because the size is fucking tiny. Because at some point, you're basically using this 8 by 8 little, like, thumbnail It's even smaller than a thumbnail. It's an 8 by 8, just like little square, and trying to predict depth from that. So of course it's just not going to be as good as if you're trying to predict depth from a 64 by 64, right? It doesn't matter that you have something like 4 times as many features to like potentially store all that depth information in. It's just the size is so tiny that it's going to be just shit with your dice or your RMSE loss. So that makes a little bit more sense. Spatial size of the ground truth label is 512. We observed that the training probes without smoothness improved the probing performance. So your probing prediction, when you're doing it kind of somewhere here, right? Somewhere here where it's still 16 by 16, right? Probing predictions have much smaller spatial resolutions compared to that of the generating images. So it's almost more like the interpolate, like resizing that back to the 512 by 512 so you can take the loss and push that gradient into the probing classifier and probing regression model. It's literally the size that's the issue. I don't get it. Are the features not contributing to the depth? They are, but there's kind of competing interests here, right? So what I was kind of referring to is that the LDM, right? The LDM has this kind of shape to it, right? It's this kind of unit. And here, it's wider. It's the height and width are wider, but it has less channels, right? So here it's 8 by 8, kind of as they were showing you here. Where is it? It's 8 by 8 height and width, but 1280 deep. And then at an earlier layer, it's 64 by 64 and 320 deep. So this dice score and this root mean squared error is you're just literally cutting off and then taking that and using this particular layer to basically predict depth or predict the binary depth. So a 64 by 64 by 320, you're going to get this score. A 32 by 32 by 640, you're going to get this score. So it's like the score keeps getting higher. So this 32 by 32 by 640 is better for predicting depth than this 64 by 64 by 320. And the 16 by 16 is better than this 32 by 32, right? And that's the kind of pattern that's going on here. But then once you get to this bottleneck, it seems to just drop, right? And that's the part that I think is a little weird. You would expect this to just be like this. It'd just be like a big U, an upside down U. Why does it drop at the bottleneck? And my hypothesis is that the bottleneck itself is so constrained, right? It just literally 8 by 8 that once you get to that level of just like Minecraftiness, you know, where it's just like kind of just a brick like that, as soon as you make the image 512 by 512 so that you can actually see how good the depth that it predicted is, it's just not going to be, it's going to be so blocky that your loss is lower than it should be, that you're going to have a higher error than you would if you just fed a slightly larger version of it, like the 16 by 16 or the 32 by 32 or the 64 by 64. Here we go, 16 by 16, 16 by 16. The bottleneck is 8 by 8. And you can see here the error 55, 55, or 51, and then suddenly 59. So even though this has more feature dimensions, it should have more information, it should be able to tell you that representation is more rich, right? The resolution of that is so, the spatial resolution is so small that I think it just fucks with the way that you're calculating the error. I don't get how the 16 by 16 is better than the 32 by 32. It's because there's more information there, right? It's that the 16 by 16 is deeper. Look at this. It has 12,080 hidden dimensions, right? So it's deeper. There's just more information, right? Think about like if you had to store the depth inside there, you couldn't really store it inside this 3 channels, but you could definitely store it inside 512, and if you could definitely store it more in 1024, right? So it's like the more the feature dimension has, the more rich that representation, that internal representation can be. So here, from the 16 by 16 layer to the 8 by 8 layer, you still have the same amount of features. The depth is still the same, but now you've halved the spatial resolution. So the reason the 16 by 16 is better than the 32 by 32 is because, yeah, it's a much smaller spatial resolution, but look at that, you're doubling the number of features. But once you get to this bottleneck, it's still the same number of features, but now you've just halved the spatial, and that's why you get this dip. Yeah, maybe more rich, but we don't know. Yeah, that is true. Rich or not rich is like a kind of like a hand wavy, like this representation is better than this representation, but like these are all just like black box representations, right? Or maybe not, right? This whole paper is basically showing you that even though it appears like a black box representation, like it actually has some notion of depth in there, and that's what these probing classifiers and probing regression model is showing you, is that I can predict depth pretty good from this internal representation, which means that that internal representation must contain some kind of depth information. It's just in a weird pattern and way that we can't interpret, but that another little neural net can very quickly interpret. Okay, what else? Is there any more pictures? No, that's it. Okay, so that's all this paper, guys. We did it. We went through it. If the 8 by 8 layer had even more features, would the dip effect disappear? Maybe. We don't know. You should test it out, Giant B. Yeah, maybe if you increase the channel dimension of the bottleneck, you don't see that dip anymore. But we don't know. They didn't carry out that experiment. All right, let me sip some yerba mate, and we'll review this paper. All right, so today we reviewed Beyond Surface Statistics, Scene Representations in a Latent Diffusion Model. This is a paper coming out of Harvard University, 9 June 2023. This is a preprint, so a better version of this paper that has been reviewed will be released at some point later, but this is machine learning, and we read papers when they are in preprint, because by the time they're released, they're already outdated. So in this paper, the authors wanted to kind of dissect and look inside a latent diffusion model, right? A diffusion model that operates on the latents of images rather than in image space, right? And the reason that diffusion models do that is because these latent spaces are smaller, so you can do diffusion faster because diffusion is pretty slow. So they kind of have an idea, or they kind of want to go in and say, okay, well, what is going on inside these latent diffusion models? Are these intermediate features, do they have some notion of maybe depth, right? And they define depth kind of two different ways. They have kind of binary depth like this, where you have foreground, background, and then they have kind of a more continuous depth, where depth can be from 0 to 1, right? And they're saying, okay, well, if I cut my latent diffusion model at some random point, and I take the intermediate representation, which is just a fancy way of saying the values of what's coming out of the neural net here, the activations of the neurons at this layer that I've cut it, right? I've like dissected the brain and then just taken all the activations that are coming out right there. And if I try to train a little one-layer linear neural net on that, and that little neural net is trying to predict the depth, can I actually do that? Can I actually train a probing classifier or a probing regression model to give me the depth given this internal representation? And it turns out that yes, you can. And not only can you do that, but you can do that with what appears to be a noise image. So these diffusion models operate on a multi-step process, right? They're basically adding and removing noise over a series of steps. And for these early steps here, it doesn't look like anything to us, right? So when we look at the beginning parts of a diffusion model, it kind of just looks like noise, right? But what they discovered in this paper is that the internal representations of the model at this point in time actually are already encoding the depth. They already have some notion of like, this is going to be the foreground, this is going to be the background, this object is in front of this object, which is in front of this object, which shows you that the diffusion model is already aware of that. It knows what's foreground and background. And this is kind of what they're showing you here, right? And the more interesting thing that they show here, another thing that they show here is that there's multiple components to this latent diffusion model. There's the actual diffusion model, which is actually removing and adding the noise, right? But then there's also this variational autoencoder, this VAE. This is the thing that takes the image from image space and turns it into this latent space and then back into the image space. So the VAE, it has notion of depth as long as the image makes sense. So if you feed this image into the VAE and you look at the intermediate layers of the VAE, yes, the VAE has some notion of like, this is the foreground and there's obviously a foreground object here and then there's a background. But if you were to take this image here and feed it into the VAE and encode it, decode it, the VAE doesn't know anything. The VAE is like, I don't know, there's no depth here and there's no information of like foreground and background, but the latent diffusion model does. And that's kind of what's creepy, is that the latent diffusion model, it knows about the depth. It has knowledge of the depth. So that was kind of a cool little insight there. Another thing they kind of do is they mess with these. So they basically, they start shifting these. They kind of like shift these intermediate representations. And by shifting them, they show that the final output of the image is also shifted in that same way. There's a little bit of weirdness where like it doesn't quite work for some of these. Right, like they do show some nice examples here where it doesn't work, where they shift the internal depth representation and then the diffusion model just kind of like hallucinates another thing that kind of still works. So this is something that I feel like would be worth kind of more of a deep dive there. Like, why does that happen for some images and not other images? But yeah, other than that, very nice little tidy, cute paper. Everything's very clean, very explainable, and I think it kind of gives us a little bit more intuition about what is going on and like how much is the latent diffusion model doing, how much is the diffusion model doing versus how much is the VAE doing, what do these internal representations really mean, right? Like they're not just statistical correlations, or as they call it at the very top of this paper, they're not just surface statistics, right? That's not what's going on here. The diffusion model actually has notions of there's objects and there's things that are in front of other things. So it's discovered this kind of semantic hierarchy of real world, which is that whenever you take a 2D image, there's going to be things that are in front of other things, and there's kind of a depth to it. So it's discovered depth, which is pretty good. I don't know. That's all I got. Good paper. I agree, Khalil. And, you know, a good paper doesn't need to have a novel algorithmic thing. It doesn't need to beat some state-of-the-art. It doesn't need to do some crazy shit. Like, just dissect a frog. You know, we're dealing with these black box neural nets. We don't really know what the fuck is going on. Like, if you can just take that little neural net frog and just dissect it and just show us, hey, I dissected the left arm, and like I figured out that if you push on the elbow here, it like changes the finger over here. Like, that's useful research. I love the interpretability research. I'm all about that. Yeah, thanks guys for the stream. Thanks Chris. Thanks Ed. Thanks Eugene. Thanks Scott. Thanks John, Mr. Z, Erdem. Who else? Future, Creative Builds, Giant B, Ed. All you guys, thanks for the questions. Thanks for the information on that DDPM versus DDIM. And yeah, I will probably no stream tomorrow. I probably will have a stream Saturday, Sunday. I'll be posting more information, but I'm going to be changing the stream schedule a little bit, probably trying to also multicast, stream to a couple different platforms, but I'll be providing more details on the Discord if you're interested. If not, see you next time and have a great day. Peace out.